Okay. So, hello. So, in the last class, we studied about the derivation of Lagrangian interpolating polynomial. So, in this class, I'll just go a quick overview of the what I taught in the last class. So, we have this Lagrange interpolating polynomial. Okay, interpolating polynomial. Interpolating polynomial. So we have just let me interpolating polynomial. Okay. So we have given consider n plus 1 set of discrete points x0 y0 x1 y1 x2 y2 up to xn yn. So here each of ya is equal to f of xi. So this is the value of the function. So the value of y is equal to f of x is given at n plus 1 grid points or nodal points. You can say points, or it's sometimes called, it is in some books you can see nodal points. Okay. So here these xi's are not equally spaced. So in the previous class we saw Newton forward and backward difference interpolation formula is based upon the equally distributed points. Okay, but here in the Lagrange interpolating polynomial is to compute the interpolating polynomial in which the grid points are not equally spaced. Okay, then we'll learn about Newton's divided difference interpolation formula. Okay, so let me write down the polynomial. So suppose Pnx is the polynomial. So Pnx. Okay, so f of x is approximated by this Pnx. Okay, so I can write down L0x f of x0, L1x f of x1, and lnx f of xn. Okay, so this is my equation 1, where L0x, this L0, L1 up to Ln are called the Lagrange fundamental Lagrange functions. Sorry, x minus x1, x minus x2 up to x minus xn divided by x0 minus x1, x0 minus x1, x2 up to x0 minus xn. Similarly, you can calculate x1. So you see one thing, in the numerator part, you don't have x0 term here. See, so you can write x minus x0 minus x2 up to x minus xn. So x2 minus x1, x1 minus x0, x1 minus x2 up to x1 minus xn. Ln x is equal to x minus x0, x minus x1, x minus xn minus 1. Okay, xn minus x0, xn minus xn1 up to xn minus xn minus 1. Okay, so these are you can see this numerator part is a function of x, whereas the denominator part is a constant term here, because x0, x1 up to xn are the given data points. Okay, so we can in general we can write li of x, okay, is equal to x minus x0, x minus x1, x minus xi minus 1, x minus I plus 1 up to x minus xn divided by xi minus x0, xi minus x1, xi minus xi minus 1, sorry, this is I minus 1, xi minus xi I plus 1 up to xi minus xn. So I can write it down the big pi, okay? So x minus xj minus xi minus xj, j varies from 0 to n, where j is not equals to I, okay? So this is the Li, okay? So now we'll do one example. Okay, in this class, I'll do one example and I will give one example more in the homework. Okay. So if you have some doubt, you will discuss in the next class. Okay. So let me write down the example for today's class. So this is called Lagrange. Let me tell you one thing. It's called Lagrange interpolating polynomial, or you can say interpolating formula also. Interpolating formula for non-equispaced points. Okay. So let us do one example quickly. Okay. So here is the example. So we have example 1. So using Lagrange interpolation formula to find a polynomial, or you can say it is a polynomial, because ultimately we are finding a polynomial. To find a polynomial which passes through the point what are the points? 0, minus 12, 1, 0, 3, 6, 4, 12. So we have the 4 points. So let us solve it. Okay, solution. Okay, here the given 4 points are, so first point is P0. Okay, this is 0, minus 12. Okay, so here x0 is equal to 0 and my f of x0 is equal to minus 12. Okay, my P1 is equal to Sorry. So 1 comma 0, P2 is equal to, sorry, P3, P6, P3, 4 comma 12. X1, 1, f of x1 is equals to 0, x2 is equal to 3, f of x2 is equal to 4, x3 is equal to 4, f of x3 is equal to, sorry, this is 6, 12. Okay.